I just want to point one thing out. It's just something about when I resolve this with current. I just got to point this out. This is awkward because current is not a vector, right? But I want to point this out. Let's say that I had a bunch of wires, okay? And I've got a wire with the current coming out right here. Maybe the wire and then I have another wire going in here, carrying that same amount of current but going the other way. All right. If I applied Ampere's law to a path that went around these guys, here's like the path I choose, right? Going around and around and around and around and around. So I close the path, okay? Then you know that this guy makes a B field that's strong near him and gets weaker as you go farther away. This guy makes a B field that's strong near him and weaker. You say in the middle here, by the way, this guy's field would be going up, and this guy's field would be going up. They would boost each other here in the middle between them. The total B field, you just add the field vectors, be going up, yeah? But further out here, this guy's field is going down, and this guy's field is going up. They would tend to, partially cancel here, you know what I mean, out here? But closer to this guy, so the field is not going to be zero, but you get the idea, right? So what I'm getting at is, there is field out here. Everywhere where this is, there is some B field. Okay, it's not a constant value. It would be icky to try to do this calculation directly, right? But what I want to point out is, if I added up B dot dl going all the way around, my answer that I would get would be 0. Mr. C, how do you know that? You can't do that calculation. That's disgusting. What's the current that's passing through this? The current that's punching through, I have an I going in and I have an I going out, and they cancel. Okay, so what I'm saying is, even though we don't think of current as being a vector, when I want to count the total current going through, current going one way, I make positive, the other way negative, and when I find the total current. So the total current for this case that's going through this path, my I total through that path is 0. Okay, just so you're aware. Okay, current's going one way, the other way can cancel out. Okay, if this wire here had a current that was twice as big as this one, this was 2I and this was I, now my I total would be I. I would have 1I as my total current. Or if this was better, if this was 3I and this was I, my total current would be 2I out of the page. When I did this calculation, it'll come out to be mu naught times 2I would be the result of this interval. So just so you know, we care about the direction of the currents, and they can add and subtract to get your total current passing through a path. Alrighty, I think that's what I needed to show you. That's pretty much Ampere's law, right? Until you do some sample problems. Wow. So Ampere's law, to my mind, is a lot easier to use than the Biot-Savart law generally. I think it's a little easier on my brain. Once I've done a few and I get the hang of what this equation is telling me, and I have this experience with doing Gauss's law stuff, and there's a lot of similar ideas, right? I compare like having a B dotted with a, here's my magnetic field dotted with a path, and in Gauss's law for electric fields, it's a electric field dotted with an area vector. But I'm choosing, in this case I'm choosing a closed path, and in Gauss's law I'm doing a closed surface. I have to make sure my surface has some current flowing through, my path has some current flowing through, just like I have to decide that I have to make a Gaussian surface that has some charge inside to get a non-zero answer. It's just like some similarities here a lot in how we work with it. And having worked with Gauss's law prepares me for working with Ampere's law. But the Biot-Savart law is just like weird in my mind. Okay, so this is no big deal. So I like this. Like I said, once you've seen some examples and so you get a feel for like choosing a path, just like with Gauss's law, we had to figure out like what's a good surface to choose. Once you've seen a few examples, you're like, oh, okay, I kind of get how this works, right? And it should be fine. So, yeah, Ampere's law. Yeah, okay, there's one last little subtopic I should just point out, okay? Because it's kind of neat, actually, right? And that goes like this. Right? This is a tiny little thing, but it matters. Here we go. So, kind of historical reasons. Let's say that I have a wire, and I'm going to run a current, I, down that wire. Okay? But look, here's another wire. We'll say that that wire is a distance A away. Okay, that's the distance between the wires. Right? Now, this wire, we'll say, also has current flowing down it. Do you want it going down the right, to the right or to the left? It doesn't matter to me. But we'll keep it simple. We'll say that this one's going to the right. I'm going to call this current B, and I'll call this current A. So it's wire A and wire B, each with their own current flowing to the right. Okay, we're going to say these are kind of long straight wires sort of things, right? Okay. So, here we go. What would happen if I had this situation set up? You say, well, this top wire, isn't that current going to make a magnetic field around itself? You say, sure. I'd grab that wire with my right hand, thumb the direction of current, the field lines would loop around like this, right? That means above the wire, up here, whoop, I'd have field lines coming out of the page, dot, 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 and then they would get farther apart as they get farther away from the wire, yeah. But on this side, I would have X's, X, X, X. You say, uh-oh. You know what that means, right? It means this guy is this is charges moving across this guy's B field lines. This purple one, this is the B field from A. And that means this wire is going to get tugged. You say, but wait a minute. Wait. This guy makes a B field of his own, doesn't he? This guy makes a B field. Grab the field, thumb the direction of the current. With my right hand, field goes with the fingers. They would come out of the page up here and into the page below. So this guy's field, I should have color-coded these. I'm going to tag this guy with a purple A and tag this guy with a pink B. Okay, so can you tell the difference on the camera? I don't know. So the point is, this guy's field will go into the page down here. Oh, look. The fields are going the same direction. They would boost each other down here below. Anyway, but up here, they're going to be going out of the page, right? This guy's field is coming out of the page, so I'd have dots here. Now, these fields aren't going to be the same strength, right? These are different currents and different distances. There'll be somewhere in here where they probably perfectly balance each other out, right? Probably, possibly, yeah. It's going to happen. There's a point where they balance out. It varies depending on how their sizes of the currents. Out here, though, they're going the same direction, so the fields would boost each other here and tend to partly cancel there. Okay, now here's the thing. This guy is going through the field that B makes, right? The magnetic field of wire B, I did in pink. The magnetic field of wire A, I did in purple. And you say, they're going through each other's fields, which means they're going to get pushed, right? There'll be that force on a current-carrying wire. Let's talk about this guy. The top one makes a purple field. This guy's a current going to the right through a purple field that's going into the page. Which way is the magnetic force on the bottom wire? So you do your right-hand rule. What's the formula again? You say, oh, that formula for the force on a wire. It's IL cross B, isn't it? Okay. And so you say, all right, in this case then, let's invent another variable. Let's say that this part, maybe these wires, maybe this wire like comes in and goes across and then goes out, and this one kind of comes in and goes. So the point is, they're just parallel to each other for this length L here, okay? This is just the part where they're parallel, and then they kind of curve off somewhere, okay? So maybe this wire like comes down from here, and this wire comes down from here or something, right? This wire comes up, you know what I'm saying? So it's just this part where they're parallel to each other. So that'd be the L in this equation. So the force, magnetic force on B, we'll say, the force on this guy, right? You say it's going to be his current times the length that's parallel there, and then crossed with the magnetic field made by A. Should I be color coding this stuff? Now you got it. Okay? You say, which way is he going to get pushed? I'm sorry. Current's going to the right. We're going to do L cross B. And the magnetic field from this guy down here is going into the page. That's these purple X's. So here we go. V, L cross B. Force is up. This guy will get pulled upward. That's the magnetic force on B by A. I shouldn't have called them B and A. I should have called them 1 and 2, so I didn't have those B's running around. Sorry about that. Should I fix that right now? I'll leave it alone for now. So I have this magnetic force attacking him up. Which way is the force on this guy? You say, I don't have to do a right-hand rule. I know Newton's third law. If wire one, see, I should have come one, two. If wire A pulls wire B up, but wire B better pull wire A down. These wires are going to attract each other. That B's for magnetic. All right, fine. I'm going to fix that because it's driving me nuts. This is. I can't fix that right. This is wire 1. This is the magnetic field made by wire 1. This is wire 2. And this is the magnetic field made by wire 2. This is the magnetic force on wire 2 by wire 1, like that, would be the current on wire 2 times the length times the B field made by wire 1. Right? Yeah? There we go. Okay. Now you see, now wait a minute. How strong is the B field made by wire 1? Well, I have a formula for that. Isn't that mu naught I over 2 pi r, right? Yeah, mu naught I over 2 pi a. So this is going to be the force on 2 by 1. One new marker. Equals, and again, it's going to be that current flowing through 2 and times that length, that the guys are parallel to each other, and there's that cross product there. And then I got the B field made by 1, but how big is the B field made by 1? That's mu naught I1, right? The field made by 1, is current in 1, over 2 pi times the distance I am apart. Well, that's A, is how far away, right? This guy is in a field that's A distance away from this wire. So how strong is this guy's field when he's A away, right? Okay, so that's it. Okay, now, there's a cross product there, right? And so you say, okay, with that cross product, that means there's going to be a sine theta. What's the angle? Well, it's the angle between the length and the field line. Well, look, the length of the wire is going this way and the field line is going into the page. You say that's just cosine or sine of 90, which is just 1. So that goes away. So what have I got? Here we go. What I have is the force on wire 2 by wire 1. You say, hey, that's going to be equal to. And now I'm just going to, this is just a 1, so I'm just going to rearrange this. It'll be that, do a marker that is clear. The magnetic force is going to be mu naught I1 times I2 over 2 pi a. And then I have that L there, right? Yeah? This is the force on wire 2 by wire 1. Hey, how big would be the force on wire 1 by wire 2? Well, it's going to be equal and opposite, right? The force on 1 by 2 and the force on 2 by 1, they're going to be equal and opposite. Newton's third law, right? Yeah? Okay, the calculation would come out the same. It would just be flipping where I have 1s and where I have 2s. I'm making the same thing out. Okay, hey, well, oftentimes you'll see it written like this. Is this on the AP formula sheet? You're like, no. Is this something you're supposed to memorize? No. This is something you derive, right? It's easy enough to do, right? Just do I cross B, and where it says B, I stick in the equation for the B field from the other guy. All right? Now, one last comment. See this length? I'm going to move it here. So oftentimes people will just talk about the force, and 2 on 1 and 1 on 2 are the same. So let's just say that magnetic force per meter that's parallel is mu naught I1, I2 over 2 pi a. So I know what the force per meter that I have parallel. Okay, that's it. Okay, so that's the force. What's this is called? It's called the force on 2 parallel current carrying wires. All right. One more comment. Okay, we had a current going here, a current going here. What would happen if current 2 was going the other way? Well, then his field would go the opposite direction, and this guy would get pushed the opposite direction. These wires would repel each other then. The force, I'd have the same equation, just the force would repel instead of attract. As a side note, just a comment, and that is wires. Right. We look at cords for things. Oftentimes, like if I went ahead and looked inside this thing, you would say there's really two wires side by side here, aren't there? And the current goes one way in one wire and the other way in the other wire, which means these two wires want to repel each other. Okay, just a side note. So they're kind of built in that way, and that's probably a good thing, because if they touch each other, they would short across each other. But I mean, they're wrapped by insulation, so that can't happen. Just a side note. Okay, hey, why did we go through this example? I mean, it's interesting. It's an application of two of the equations at the same time, right? Field strength and force on a wire in a magnetic field. We talk about it because this is how the unit for current is actually originally defined, the ampere, right? You say, no, wait a minute, wait, what do you mean current's defined this way? You say an ampere, that's defined in terms of coulombs. An ampere is a coulomb per second, right? That's because this is how the coulomb is defined. Do you remember way back when we first talked about charge, and I talked about how a coulomb is a huge unit of charge, it's a ton of charge? Why is the coulomb so big? We're always using like microcoulombs and stuff in calculations. Why is a coulomb so big? Because they wanted to have enough charge flowing that it would make something you could easily measure. Like in the lab, I know, oh, I had a coulomb of charge per second flowing. That's what an amp is, right? So the coulomb, a coulomb per second is an amp. It's actually defined in terms of like setting up this arrangement and then measuring that force. So having enough current, enough coulomb of charge per second flowing, that this force is something we can measure. They said, okay, so if I have two wires, right, and I set them 1 meter apart, getting on? And I put currents, what I'm gonna call 1 amp in each of them, right? If I do that, if that is in fact 1 amp, 1 coulomb per second going through, then my force per meter, per 1 meter, is going to be 10 to the minus 7 newtons, which is about the smallest force they figured they could reasonably measure. Hey. Oh wait, I'm sorry. My force is going to be, hang on a second. It's going to be 2 times 10 to the negative 7 newtons. Sorry, I know it's defined in a weird way. What? How do I know it's that? Because what's mu naught? 4 pi times 10 to the negative 7. Ta-da, right? And 2 pi, I just get 2 times 10 to the negative 2 times, right? That's the way. All right, I know it sounds dumb, but kind of weird. If they wanted to define these units for charge in terms of something you could actually physically test in the lab, can you see charges? No. They needed something they could actually physically do to say this is how much charge we have. In this case, it was in terms of the force here between two parallel current carrying wires and how much charge per second is flowing down the wire. That's the way they defined it. And so this setup is how the coulomb, the amp, and then ultimately the coulomb is defined. Weird, huh? Okay, good enough. And also why that unit comes out the way it does, right, for mu, that value for mu naught. Yeah. Okay, I know, it's still a little strange. Why that value, 2 times 10 to the minus 7, I don't know, yeah. Okay, like I said, it's probably about the smallest force they figured they could accurately measure at the time, or precisely measure at the time. Okay, hey, where are we doing now? That's it, that's Ampere's law. Hey, that's finding magnetic fields. Is there anything else little that I gotta remember to talk about? I think that's it. I think that's pretty much it. I think we're ready to go to the last big chunk of the course, which is called electromagnetism. Okay, so that's it. This is a good spot in this video here. Are there calculations in your packet on Ampere's law? Yes, there are. Did I post solutions for them? I'm going to do that with this video. So there we go. All right, cool. All right, see you next video. Email me with questions, right? Okay, happy to talk through any problems you have.